Hi guys, and welcome back to the video series on ODEs. And in this video, we'll be talking about the variable separable method. So firstly, what is this technique about? Which is the second of the 5 techniques we'll be learning in this video series. For this variable separable technique, it's mainly for differential equations which have both the variables on the same side of the equation. For example, we have x's and y's on the same side of the equation. And secondly, the x's and y's, or the two variables, must be multiplied or divided by each other. They cannot be linked by a plus or minus sign. So these are the two conditions. Because the two variables are on the same side of the equation, we are unable to use the previous method we've learned, which is direct integration. To solve the DE, we will need to separate the variables into their respective sides of the equation. Then we can integrate them to their own terms. Alright, but basically we'll be using division or multiplication techniques to separate both variables to both sides of the equation. So let's dive right into some examples. First example we have is this. dy dx equals to xy. So it fulfills the condition that both variables are on the right hand side and they are multiplied to each other. So we will be using multiplication and division operations to separate the variables. And in this case, we will divide both sides of the equation by y. Okay, so we'll divide it 1 over y, dy dx, equals to x. Why didn't we shift the x over instead? You will see why in the steps to come. So now we're going to integrate both sides, but with respect to which variable? So we would integrate them with respect to x. And I'll show you how the variable separable method works. So we'll do a dx at the end, same for the right hand side. As you can see, we can kind of treat them as fractions, the dy dx and the dx. So we can cancel it off, although in the working it's not recommended to write this because it's quite much wrong. Okay, so we can cancel off the dx's, and you notice we are left with a dy on the left hand side. And doesn't this fulfill the technique, the top, that we are at the end of the day, we are able to integrate both sides with respect to their own terms. So we will follow through with the next step. Integrate 1 over y dy equals to integrate x dx. And let's do now we can integrate them directly, pretty much. So we have a ln mod y on the left hand side equals to a x squared over 2 plus c. Right, once again define where c is any arbitrary constant. Now that we have this, we just need to simplify to make y the subject. Using our ln rules, we will be converting the logarithmic form to the exponential form. So raise it to the power of the natural base. So we have y equals to plus minus, because of the mod sign, we're going to open the mod sign up, so we have a plus minus sign, of what? The natural base raised to the power of x squared over 2 plus c. So the c goes into the power, alright? And let's see how to further simplify this. We can use the index rule, okay, to split the plus c out of the power. Let me show you how it's done. Alright, so we can have a nice e to the power of x squared over 2 multiplied to what? Plus minus e to the power of c. Okay, so your indices rules. And we can actually let a equals to plus minus e to the power of c. And as such, we can substitute out to get our nice, neater, simplified answer of a e power x squared over 2. And that is our answer right here. Alright, and we will move on to the next example, which is this question. A cup of coffee is left in a room with a constant temperature of 20 degrees Celsius, so like the surrounding temperature. The rate at which it cools is proportional to the difference between its own temperature and the room temperature of 20 degrees. Suppose the coffee was initially 90 degrees, after 10 minutes it cooled to 60 degrees. Find the temperature of coffee as a function of time and determine the temperature after 20 minutes. Okay, let's break down the question here. Okay, suppose the coffee was initially at 90 degrees. Let's let the time that is left to cool be time left to cool be T minutes, and the temperature be T degrees Celsius. Okay, big T and small t. Alright? So we have two known points here. Okay, number one, initially means to say that the small t has a value of 0. 0 minutes has passed. And the temperature, big T, equals to 90. Next known point is here. After 10 minutes means to say small t equals to 10. Temperature is now 60 degrees. So big T is 60. Just to break down the question even more. Alright? Let's start approaching the question. We have to come up with our own differential equation now. We can start our working by using this statement to help us. The rate at which it cools, in other words, we will call it dT over d small t. The change in temperature over change in time is proportional to the difference between its temperature and room temperature. So if we add a proportionality constant k here, what's the difference between its temperature and room temperature? It makes sense that we take the big T, which is the higher temperature, minus the lower temperature, 20 degrees. And because it's cooling, the direction of temperature change is downwards, it's negative. Therefore, we will put a minus sign in front of the proportionality constant. That is our differential equation that we have to solve for this question. And let's now acknowledge the fact that we have to use the variable separable method. Take a look. Although we don't have a term in small t, we can take k or negative k as that term in small t. And since the term in small t and big T are both on the same side of the equation, the right hand side, and both are multiplied to each other, that necessitates the use of the variable separable method to simplify this differential equation. As such, we will be bringing over the big T term first. Take 1 over t minus 20 multiplied to the big T over the small t equals to negative k. So the trick is to follow the variable which is on top of the dt over dt. So in this case, the big T is on top. So that means we will shift all the big T's to the left hand side. Having done this, we are ready to integrate both sides of the equation to the small t because it's at the bottom of that dt over dt. So we integrate t minus 20 the big T over the small t. With respect to small t, do the same on the right hand side. Negative, we can put it outside of the integral sign, d small t. And you notice that it cancels off. We are left with this equals to negative integral of k small t. Doesn't it look much simpler now? Okay, now we can integrate both sides of the equations with respect to their own terms. And on the left hand side, it will be a ln t negative 20. Okay, equals to negative kt plus c, where c is ... same as the question above. And you may be wondering, why didn't I put a mod sign for the ln function on the left? Because t, it's always gonna be greater than 20. It only makes sense because the coffee is cooling down. Means the coffee is warmer than the room temperature of 20 degrees. Therefore, t minus 20 will always be greater than 0. And it doesn't make sense if it dips below 0. Why will it cool below room temperature? Okay? So with that said, we can remove the mod sign, put it as a bracket. And let's start to solve for two constants. We have k, the proportionality constant, and c, which is the integral constant. So let's use one of the known points first. T equals to 0, big T equals to 90. So let's do this. So when t equals to 0, big T equals to 90. How do we substitute this in? Ln 90 minus 20 equals to c. So we have c equals to ln 70. That is one constant solved. So let's use the other known point, which is small t 10, big T 60, to solve for our constant k. Small t equals to 10, big T equals to 60. Okay, and we're going to substitute these values into the equation. ln 60 minus 20 equals to negative 10k plus ln 7t. Okay, then we can simplify this. Let's use some logarithmic rules. Ln 4t equals to negative 10k plus ln 7t. We can bring the 10k to the left hand side, equals to ln 7t minus ln 4t. And because they are connected by a negative sign, we can change them to a divide. Ln 7t over 4t on the right hand side, which simplifies to ln 7 over 4. So we have 10k equals to ln 7 over 4. Make k the subject, we have 1 over 10 ln 7 over 4. Let's substitute both k and c values into the big equation now. So we have ln t minus 20 equals to negative k, which is negative 1 over 10 ln 7 over 4 t. So we have this. Okay, put it in a bracket to avoid confusion. Now we have the plus c, which is ln 7t. And we just have to simplify to make big T the subject, since the question is asking for the temperature of the coffee as a function of time. So temperature will be the subject. Let's start by combining our lns first. So we have ln t minus 20. Right hand side, we can simplify this to ln 7 over 4 raised to the power of negative t over 10. Because the negative t over 10 was first multiplied to the ln 7 over 4. And we can bring this constant up to the power based on the logarithmic rules. We are left with a plus ln 7t. One more step to combine these two lns on the right hand side, equals to ln 7t multiplied to 7 over 4 negative t over 10. And with that, we can remove the lns. We are left with this. Okay, make t the subject. We get this 20 plus 7t, 7 over 4 negative t over 10. That is our final answer. So once again, the first example is more of a general solution where we can sub any constant in A that satisfies the requirements. Question 2 is more of a particular solution where we used the known points. In this case, the question gave us 2 known pieces of information. And then we can substitute and solve for our constants k and c to get our final particular solution. With that, hopefully you've gotten a better understanding of the variable separable method from this video and the use cases. And I'll see you in the next video for the homogeneous equation substitution method. See you there.